Section 2 is entitled Series and Convergence. Now, series is the sum of the sequences. Suppose you just want to find the first 5 terms of the sequence of partial sums. Suppose you have the summation that n goes from 1 to, say, infinity of 5 over 2n minus 1. You want to find the first 5 terms of the sequence of the partial sums. Well, first n is 1. 1 minus 1 is 0. You get 5 over 2 to the 0 plus, now n is 2. 2 minus 1 is 2. Let's try that again. 2 minus 1 is 1. And now n is 1, 2, 3. 3 minus 1 is 2. You get 5 over 2 squared. And if you start seeing the pattern, 5 over 2 to the 3. 5 over 2 to the 4. And so on. Now, the partial sums, find the 5 partial sums. First of all, let's just work this out. 2 to the 0 is 1, 2 to the 1 is 2, 4, 8, let's keep multiplying by 2. 5 over 16. Find the first 5 partial sums. So first, you just add up the first term, which is just 5. And we call that S sub 1, the first partial sum. The sum of just the first number. The sum of the first 2 numbers. Well, add the first 2. 5 plus 5 over 2. Okay, this is 7.5. I'm more concerned about this, how you add 2 numbers. I'm sure you know how to do that. S sub 3 is the sum of the first 3 numbers. It's 5 plus 5 over 2 plus 5 over 4. I guess it's 8 3/4. I added 1 1/4 to the number above. Because this is S2, 7.5. 8 3/4. S sub 4, that's S sub 3, the sum of the first 3 numbers plus the 4th number, 5/8. It's 8 6/8 plus 5 more 8s. That's 11/8. That's 9 and I guess 3 over 8. And S5 would be add on 5 over 16. That's the partial sums. I listed the first 4. 5, 7.5, 8 3/4, 9 3/8. And somebody might ask, well, is this convergent? Okay. As you add on more and more, is the sum convergent? This here is called a series. A series is when you add up the terms of the sequence. The sequence is just a list. The sequence was 5, 5 over 2, 5 over 4. I'm getting them from right above. 5 over 8, 5 over 16. Now we can talk about if the sequence converges or not. And yes, we're taking 5 and we're dividing by more and more and more. Here we divided 5 by 1, and then by 2, and then by 4, and by 8, and 16, and eventually something like 1 billion, and then 1 trillion. it's going to 0. That doesn't necessarily mean the sum. That doesn't mean if we add up these terms, it's going to converge. It's a necessary condition. It's a necessary condition to converge. If the terms don't get close to 0, then it won't. And when you add them up, it won't converge. If the terms are, at some point, the terms are near a half. Well, a half plus a half plus a half plus a half forever going to converge. Think about that. If the terms start getting close to a half, that means they'll all be bigger than a quarter. If they're really getting close, if it converges to a half, that means the terms far out there are getting closer and closer to a half. That means they're all bigger than a quarter. Well, I may not know what the first terms are, but at the end, it's going to be bigger than the sum. Will be bigger than the sum of all the terms. The sum of the a sub n's will be bigger than a half plus a half plus a half forever. You can factor out a half. You get 1 plus 1 plus 1 plus 1 forever. That's infinity. Half times infinity is infinity. And I didn't even add on the first 20 billion terms yet. I'm just looking at the end. So the sequence must converge to 0 for the sum of the terms to converge. Okay? But it still may not converge. It's mandatory. It's a must. It's necessary that the sequence converge to 0 for this series, the sum of the terms, to converge. But it's not sufficient. It's not enough. There are cases where the terms get close to 0, but not very quickly. So it still adds up to infinity. Okay, with enough of this theory, let's do some of the problems. So finding the partial sums are straightforward. List out the terms. S1, just add up the first term. That is, write down the first term. That's S1. That's what S1 equals. S2 is add the first 2 terms in their sequence. S sub 3, add the first 3 terms. S sub 20, add the first 20 terms. Okay, so over here, I want us to verify that the infinite series diverges. It's an infinite series because we're adding up forever. A half plus 2/3 plus 3/4 plus 4/5 plus 5/6 forever. Okay, why does that converge? Well, the terms are bounded below. The terms 1/2, 2/3, 3/4, 4/5, 5/6, they're all bounded by a half. All the terms are either bigger than or equal to a half. What a coincidence. I didn't plan it this way. So we have a half. This mess is bigger than a half plus a half plus a half plus a half, etc. A half is equal to a half. But 2/3 is bigger than a half. 3/4 is bigger than a half. 4/5 is bigger than a half. 5/6 is bigger than a half. 6/7 is bigger than a half. 7/8 is bigger than a half. And so on. The problem is that this equals infinity. A half plus a half plus a half plus a half. That's infinity. I mean, 1 plus 1 plus 1 plus 1 forever. That's infinity. And the line above is even bigger, so it diverges. One test is to show that the series does not go to 0. Okay, 1/2, 1/3, 2/3, excuse me, 3/4, 4/5, etc. A sub n. Well, the numerator is always that number. That is, the first term has a 1 on top, the second term has a 2 on the top, the third term has that strange looking 3 on the top, the fourth term has a 4 on the top. N. Whatever the subscript is, that's what the numerator is. And the bottom is always one more. The limit of a sub n as n goes to infinity. If this limit is not 0, then this series, the sum, you have sequences that just, you list the terms. When you list things, you put parentheses between them. When you add them up, we call it series. The limit of a sub n. A sub n is n over n plus 1. Since the degrees are both the same, the highest degrees are both the same, you just divide the understood numbers in front of them, and you get 1. This is not 0. That implies a sub n diverges. I'm not saying if you get 0, I'm not saying if this limit is 0 that the series must converge. I'm saying if it's not 0, then it won't converge. If it is 0, sometimes it will converge, sometimes it will not converge. But if you don't get 0, forget about it, it's diverging. If the nth term, the a sub nth term, is not approaching 0, well then it's not going to converge. If these terms are getting closer and closer to 1, way out there. So initially, I don't know what we have initially. I don't know what we have initially. But you know what? Later on, they're all going to be bigger than a third. Because they're getting closer and closer to 1. They're all getting bigger than a third. And if you add a third forever, that diverges. And all I do know about these unknown numbers is they're positive. Because n is positive, and 1 more than n is positive. Divide positives, you get positives. Okay? So at some point, they'll all be bigger than a third. And then you add on more, a third plus a third forever is infinity, and you add on some of these unknown positive numbers, you get a little bit more than infinity, which is infinity. The n terms must be approaching 0 to possibly converge. If they don't approach 0, it diverges. This is the divergent test. How do you tell if a series diverges? Show that, one way is to show that the a sub n does not approach 0. You have the summation of n factorial over 2 sub n. 2 to the n. And n goes from 1 to infinity. How would you show that this diverges? Now, you can't, so this is always a sub n. You can't possibly, you can't take the limit. I mean, have we ever taken the limit with the factorial? With the factorial. I mean, a larger number factorial, larger and larger number factorials is infinity. A billion factorial is really large. 20 billion factorial is larger. 100 trillion is larger. 2 to large numbers is infinity. Okay, use L'Hopital. That's the ticket. We don't know how to take the derivative of n factorial. One can even argue we only know how to take derivatives of continuous functions. 2 to the n. See, 2 to the x may look like this, but 2 to the n, where n is positive, only has some of these points. We can't even really talk about derivatives. Necessary condition for derivative to exist, the function be continuous. Okay, so we can't do that. Now, you have to think about it. We know that the terms are positive. Let's look at the first few. I mean, when it comes to the numerator, let's work out the numerator. You get 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. The bottom, 2 to the 1, 2 to the 2, 2 cubed. You get this. This is a half. This is also a half. This is bigger. It's 3/4. This is more than 1. That's more than 3/4. This is more than 3. It's more than 3. Seems to be getting bigger and bigger and bigger. If I can show that the terms are getting bigger and bigger and bigger, then it can converge. Then it can converge. But they're not always getting bigger. I mean, they didn't get bigger here. They stayed the same. So the question is a sub n plus 1 bigger than or equal to a sub n? That's what we want to show. Instead of n, remember, this is a sub n. That is a sub n. A sub anything, you replace the n with the anything. A sub this. Instead of n, we put n plus 1 factorial over 2 to the n plus 1. Now, since these are all positive quantities, you can move them around and you don't have to change the sign because something's negative. I can move this into the bottom. It's called division. I can move this into the top on the other side. So now I have n plus 1 factorial divided by n factorial. Is it bigger than or equal to 2 to the n plus 1 over 2 to the n? Well, n plus 1 factorial means n plus 1 times 1 less, which is n, times 1 less than n, times 1 less than that, and n minus 1. Let me write it more to the right, to the left, excuse me. It's n plus 1 times n minus 1 times n minus 2, all the way down to 1. Now we divide this by n factorial, which is n times n minus 1 times n minus 2, all the way down to 1. This cancels out, and you just get n plus 1. This mess here is just n plus 1. When you're dividing, and the bases are the same, they're both 2, you subtract the exponents. If you have n plus 1 and you take away n, you just get 1, which is 2. Now, is this symbol true? Remember, n is 1 or more. N starts at 1 and it goes higher and higher. When n is 1, this is 2. And yes, 2 is greater than or equal to 2. And when n is more than 2, like 3, well, if n is more than 1, then it's 2. 2 plus 1 is 3. That's more than 2. Then it's 3. 3 plus 1 is 4. That's more than 2. Yeah. This symbol is correct. This symbol in the middle is correct. In fact, they're all correct. That's enough to show that it diverges. The terms are all a half or more. Okay, that's enough to show that it diverges. Do have one little typo. It should say up here plus and so on. Now, these are all of these terms are a half or bigger. A half is bigger than or equal to a half. It equals. 2/4 is bigger than or equal to a half. 6/8 is bigger than a half. The next one is bigger than a half. They're all now bigger than a half. That diverges. That diverges. Okay? I showed that the next term is bigger than the preceding term. Unless the terms are negative. The terms are sequenced for now only have positive terms. Now, the question is, how can the terms be getting bigger and bigger and approaching 0? How can positive terms get bigger and bigger and approach 0? They can't. Oh, it diverges. This series diverges. This series diverges. Just try another one. Verify that the infinite series converges. 2 plus 3/2 plus 9/8 plus 27/32 plus 81/128 and so on. Now, if the first few terms doesn't fit our pattern, that's not so terrible. That's not so terrible. Possibly the first term will fit our pattern, but let's look at it more carefully. This numerator is 3 to the 1, and then 3 to the 2, and then 3 to the 3, and then 3 to the 4. All I'm getting at is that what's in the bracket converges, but when you add 2 to it, it'll also converge. The 2 at the beginning. Okay, so we have the numerator, at least for what's in the brackets. 3 to the 1, 3 to the 2. Now, the denominators. We keep multiplying by 4. We keep multiplying by 4. Okay? So, this is 2 plus, now, it's the sum, and we'll say n goes from 1 to infinity. The top is 3 to the n. The numerator is 3 to the n. Because when n is 1, you get 3 to the 1, and then when n is 2, you get 3 to the 2, and 3 to the 3. Now the bottom. The bottom, we keep multiplying by 4. So we multiply n by 4. And when n is 1, 4 times 1 is 4. So 4n. You'll get 4, and then when n is 2, you get 8. And when n is 2, you get 30. When n is This is when n is 1, and then n is 2. We want to multiply by 4. We want to keep multiplying by 4. So we take 2, we multiply it by 4, we get 8. And then we multiply that by 4, we get 32. Okay, so, excuse me. We're multiplying by 4. 4 to the n. Now, how silly of me. 4 to the n. When n is 1, you get 4. When n is 2, you get 16 4 times. When n is 3, you get 64 4 times. That's kind of what we want, except we don't want 4, 16, 64. If we divide each of these numbers by 2, then we're getting what we want. 2, 8, 16. So it's half of 4 to the n, which just happens, so it's 2 plus, now instead of dividing by half, you can multiply by the reciprocal. 2 times 3 to the n over 4 to the n. Okay. And now we're ready to really start progressing here. This constant 2 can come in front of the summation. It's 2 times the summation of 3 to the n over 4 to the n, and then goes from 1 to infinity. But remember, a to the n divided by b to the n, this is just a over b to the n. That is, we have 2 plus 2 times the summation of 3/4 to the n, as n goes from 1 to infinity. Okay. Now, the problem we have right now is we have this rule that says that the summation of r to the n, as n goes from, I think, 0. Let me look that up really quickly. It should be right there. Now, n equals 0 to infinity. This equals 1 over 1 minus r, providing r in absolute values less than 1. Now, our problem is that we're starting at 1. Now, if I were to factor out the 3/4, then this would be 3/4 to the n minus 1, and goes from 1 to infinity. In fact, let me erase the rule I just stated, and due to space, let me move this over. Okay, this is called alphabet soup. It's just silly stuff that is a pain to handle. I broke off for 3/4 and goes from 1 to 1/4. In fact, I can bring the 3/4 in front. 2 times 3/4 is 3/2. And now n goes from 1 to infinity. Why am I doing this? Because my rule says that as long as what's in the bracket is less than 1, this power must start at 0. When n is 1, it starts at 0. I mean, this is the same as 2 plus 3 over 2. Now, over here, believe it or not, I'm going to take away 1 from both sides. I'm going to take away 1 from both sides. N equals 0, n equals 1 means n minus 1 equals 0. If n equals 1, then n minus 1 equals 0. Infinity of 3/4 to the n minus 1. Alright, let me erase the middle. And now we are in good position. Now, what I can do is I can call n minus 1 whatever I like. Today, I like to call it k. So I get 2 plus 3 over 2, summation as k equals 0 to infinity of 3/4 to their k. But that's exactly the rule I stated. I said the summation as n. It's a dummy variable. As n goes from 0 to infinity of r to the n. This is 1 over 1 minus r. So long as r is less than 1. This is a dummy variable. If n is 0, then that's 0. Then n is 1, that's 1. Then n is 2, and that's 2. Same thing over here. Now, I mean, if I call this k instead, if I called it k instead, it's not going to matter. First, k is 0, so the power is 0. Then k is 1, and now the power is 1. It doesn't matter whether I call it k or n. Okay, so now let's just do it. So it's 2 plus 3/2 times this. But that is 1 over 1 minus 3/4. 2 plus 3/2 times 1 over 1 minus 3/4 is 1/4. And instead of dividing the 1 by 1/4, you can multiply the 1 by the reciprocal. Okay. 2 is 2. 3 over 2 times 4 is 6. Times by 1 is 6. This is 8. 3 over 2 times 4. 2 goes into 4 2 times. You get 6. And then multiply by 1 and you still get 6. 2 plus 6 is 8. That initial problem equals 8. This sum, forever and ever, I can tell you exactly what it equals. It equals 8. What I would like to spend a moment on, now I don't know if it's worth the time, but let's see if that first term really was part of this. Let's see if it's really was part of it. If you divide the bottom by 4, if you divide this bottom by 4, you get 32. If you divide this by 4, you get 32. You get 8, excuse me. If you divide 8 by 4, you get 2. If you divide 2 by 4, you get 1/2. So that means this first term should have 1/2 in the bottom. Okay? And the top, 3 to the 4th, 3 to the 3, 3 to the 2, 3 to the 1. The top should be 3 to the 0, which is 1. Instead of dividing by 1/2, you can multiply by the reciprocal. That's 2. This first term even lived up to everything. It even lived up to everything. I could have said that it's the summation of 3 to the n, but here n starts at 0. And the bottom was, it was 1/2 4 to the n. So instead of dividing by 1/2, you could multiply by the reciprocal. 3 to the n over 4 to the n. And yeah, this is a lot easier. The 2 comes in front, and the 3 to the n over the 4 to the n is just 3/4 to the n. But now the nice thing is n is starting at 0. So then you get 2 times 1 over 1 minus 3/4, which is 1/4 in the bottom. So you get 2 times 1 over 1/4. But 1 over 1/4 is 4. Noah, 2 times 4 is 8. It is a bit quicker to do it that way. But you got to be really, really on top of things to realize that the first term, too, fit into that formula. It fit in like a glove, but you had to fit it as well. You had to do the fitting. Ever try something on? It's hard to put on maybe, but once you get it on, it's like, oh yeah, this fits well. This fits nicely. Remember that that formula we just used is when r is less than or equal to 1. For example, how would you show that this diverges? How would you show that this is diverges? Well, the summation of odd is n as n goes from 0 to infinity. We know that this diverges if the absolute value of r is bigger than 1. This statement means r is bigger than 1 or r is less than negative 1. Okay. Since r is 4/3, which is bigger than 1, that implies it diverges by this rule right here. We know it converges if the absolute value of r was less than 1. What does it mean the absolute value of r is less than 1? This means that r is between negative 1 and positive 1. Should ask what happened at 1 and at negative 1. And if r is 1, I think it's easy. The summation of n goes from 0 to infinity of 1. 1 to the n. So you get 1 to the 0, which is 1, plus 1 to the 1 is 1. 1 squared is 1. 1 cubed is 1, etc. This is 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. This diverges. It diverges. Negative 1 is a whole nother story. That's when the signs are going to alternate. So that too diverges. What if you needed to do this one? The summation as n goes from 1 to infinity of 1 over n times n plus 1. Does this converge or diverge? When you can plug in the terms, you get 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, etc. Well, the bottoms are getting smaller. Excuse me. The bottoms are getting bigger. 2, 6, 12. I mean, we keep making the numbers bigger in the bottom. The first number got bigger, the second number got bigger. The first number got bigger, the second number got bigger. The bottoms are getting bigger. The tops are all 1. So the terms are getting closer to 0. If they weren't getting closer and closer to 0, the sum of their terms, that is their infinite series, would diverge. But if the terms are getting closer to 0, then we don't know. So we have to try something else. I would think partial fractions. 1 over n plus 1 over n plus 1. This, excuse me. 1 over n times n plus 1 will equal to some constant over n plus some constant over n plus 1. Now let's work here and get a common denominator, which is n times n plus 1. On the left, we multiply by n plus 1 over n plus 1, 1. And on the right, we multiply by n over n. So we get an plus an plus a on top, plus bn, plus bn. Combine the n's, we have a plus b of them, plus the number a. Well, this must equal this. And since the denominators are the same, then the numerators must be equal. 1 must equal a plus bn's plus a. You have to be mathematically mature enough to realize that 1 is 0 n's plus 1. That is, this must be 0 and this must be 1. Well, if a is 1 and a plus b is 0, bring the a over. That is, solve for b. b is negative a. b is negative a. But that's what a is. It's 1. So a is 1, b is negative 1. Okay, so this is equal to a over n plus b over n. Excuse me, it equals the summation of that. Now, let's see what happens. I just hate having the first term being the negative. You have 1 over n plus 1 minus 1 over n. And you have n going from 1 to infinity. Alright, so let n be 1. So you have 1 over 2 minus 1 over 1 plus, now n is 2. You have 1 over 3 minus 1 over 2 plus 1 over 4 minus 1 over 3. All the way down to, say, n is k. You have 1 over k plus 1 minus 1 over k, etc. But look what happens. It's really unbelievable. A half minus a half leaves. A third minus a third leaves. The quarter minus the quarter will leave. And remember, like the second in here, the second one canceled out earlier. The second one canceled out earlier. The 1 over k canceled out earlier. And this is going to equal to the limit as k goes to infinity. We want this to go on forever. That is, I don't even have to write plus and so on. So what survived? What survived was the negative 1 plus this way out there. But that term that keeps surviving until you add on the next one. See, the 1/3 survived until you added on the next term, and then it canceled out. The 1 over k plus 1 survives until you add on the next term. Like, for example, the next term would have been 1 over k plus 2 minus 1 over k plus 1. And now the 1 over k plus 1 cancels. Okay, but if we keep pushing this out to infinity, it doesn't matter. This goes to 0. The sum is negative 1. Partial sums did this. This is called a telescoping series because every other term canceled out something from the earlier one. It's negative 1. That 1 over k plus 1 term that keeps surviving, as you go out further and further and further, it doesn't matter that it survived because it's 0. It's approaching 0. Okay, so let's do some standard ones. Suppose you have this. So let's find the sum. N goes from 0 to infinity of -1/3 to the n. Remember that the summation is n goes from 0 to infinity of r to the n is 1 over 1 minus r if r is less than 1. Absolute value of r. Our case, r is -1/3. And the absolute value of that is 1/3. Okay, that's less than 1. That's less than 1. So this is equal to 1 over 1 minus r. If r has its own negative sign, whatever, you have to put it down. 1/3. So it really becomes 1 plus 1/3, which is 4/3. 1 plus 1/3 is 1 1/3. 3 times 1 is 3, plus 1 more, 4/3. And instead of dividing by 4/3, you keep the top the same, which is 1. You change division to multiplication, and you flip over the second number. And 1 times 3/4, 3/4, and that's your answer. If you added up those numbers, it'll add up to 3/4. And since it was a negative number to a power, to the nth power, the signs will alternate. But it still adds up to, I think I said 3/4. One more. Suppose you have the summation as n goes from 2 to infinity, and you have 1 over n squared minus 1. N squared minus 1 can be factored to n plus 1 times n minus 1. Prime candidate for partial fractions. 1 over n plus 1 times n minus 1. I want to write it as some number over n plus 1 plus some number over n minus 1. Now I want to write this second term, or sum, with a common denominator, namely n plus 1 times n minus 1. Top and bottom for the first fraction gets multiplied by n minus 1 over n minus 1. The second fraction gets multiplied top and bottom by n plus 1. So you have a times n minus 1, which is an minus a, plus b times n is plus bn plus b. The bottom stays the same, n plus 1 times n minus 1. The numerator kind of run out of space, so let me put it up higher. I have an's plus bn's. That is, I have a plus bn. I hate writing negative first. Then I have b minus a plus b minus a. And that numerator, since the denominators are the same and they're equal, fractions are equal, the numerators must be equal. 1 is nothing more than a plus b times n plus b minus a. But 1 is 0 n's. Why did I want to say that? Because I have n's. This must be 0, and the plus, the constant, plus, must be 1. The constant must be 1. So what we know is b take away a is 1, and b plus a is 0. I wanted to write it as b plus a. That way the b's and the a's are underneath one another. If I add these, I get 2b is 1. So b is a half. And if you add on a to b, you get 0. But a is negative a half. Okay, so I'm going to erase most of this. N plus a over n plus 1. A over n plus 1. So it's a negative a half over n plus 1 plus b, which is positive a half over n minus 1. Okay, I'll factor out the half. I'll factor out a half. And I like to say positive stuffs first. So I'm going to say plus 1 over n minus 1 minus, that minus 1 over n plus 1. And this is going to telescope. It's going to telescope. And since it's going to telescope, let me write it on the next line. We have a lot of space. So 1 half. Well, first, n is 2. So 2 minus 1 is 1. You get 1 over 1 minus the third. 2 plus 1 is 3. 2 plus 1 is 3. This was 2. Now n is 3. 3 minus 1 is 2. Minus, and 3 plus 1 is 4. That was n is 3. Okay, now n is 4. So we have 1/3 minus a fifth. That was when n is 4. Now n is 5. So you have 1/4 minus or 1/6. Let's actually see how to do it. And then you have a fifth minus a seventh. Then you have 1/6 minus an eighth. And then eventually you have 1 over k minus 1 minus 1 over k plus 1. This here was when n was 7, and this here is when n is k. Now n is k plus 1. K plus 1 minus 1 is k, and k plus 1 is k plus 2. Forever and ever and ever. Now, let's see what happens. 1/3 goes with 1/3. 1/4 goes with 1/4. 1/5 goes with 1/5. 1/6 goes with 1/6. 1/7 will go with 1/7. I think what we needed were the last 3 terms. We needed to have the last 3 terms. This is k plus 1. Now if we have k plus 2, 1 over k plus 1 minus 1 over k plus 3. Etc. So the k plus 1 will cancel. The first term, like 1 over 5, canceled out earlier. 1 over 6 canceled out earlier. 1 over k will cancel out earlier. 1 over k minus 1 canceled out earlier. 1 over k canceled out earlier. Now, the second term, like 1 over 3. 2 sums later, it canceled out. 1 over 4. 2 terms later, it canceled out. So the 1 over k canceled out 2 terms later. Okay, now, if you take the limit, as k goes to infinity, what survived is the limit as k goes to infinity. What survived is the 1/2 all the way in front, the 1 over 1, which is 1, plus the half, and minus 1 over k plus 2, minus the 1 over k plus 3. But you know what? As k goes to infinity, both of these go to 0. So the answer is just 1 plus a half, or 3/2. You add those up, you get 3 over 2. I mean, you actually could add them up because it's infinite. But you add them up for a while, you'll start getting closer and closer to 1.5, which of course is 3/2. At the beginning, you had a couple of terms survive. At the end, they all cancel out. They all cancel out. Eventually, those last terms got canceled out. Well, you can take the limit and say there's 0 anyway. Here's a silly problem. Somebody asks you to find out the sum of, say, 1 over 4 to the n plus 1 over 5 to the n. Remember, sigma distributes across equal signs. That is, this is just the summation of 1 over 4 to the n plus the summation of 1 over 5 to the n. And I forgot to tell you, n goes from 0 to infinity. Okay, well, 1 is the same as 1 to any power. Call the power n. 1 is 1 to the n. So this is really the summation of 1/4 to the n plus the summation of 1/5 to the n. And n goes from 1 to infinity. So it goes from 0 to infinity. So for the first sum, you get 1 over 1 minus 1/4. Plus the second one is 1 over 1 minus 1/5. You can multiply the top and the bottom by 4. 4 times 1 is 4. And here you get 4 minus 1 is 3. Okay, I mean, for this one, you can say it's 1 over 4/5, which becomes 5/4, or you can multiply top and bottom by 5. 5 times 1 is 5 over 5 minus 1 is 4. And I guess this is 31 over 12. 31 over 12. Yeah. I just want to show you one little thing. It's a nice little trick. Some of you may be saying, well, what do you mean you can add up numbers forever? Positive numbers forever and ever and ever. And it adds up to a constant. It converges. Well, here's a nice little argument. Maybe I should have given it earlier. But let's add up the area of this. Let's add up the top half. Half. Suppose the area, the whole area, is 1. So this is half. This is half. And then I take the remaining half and I cut it in half. That is, this piece is 1/4. 1/4. And the blank space is also 1/4. Well, if I cut it in half, then that will be 1/8. And the blank spot, the blank piece, is also 1/8. If I cut it in half, then what I just shaded in will be a 16th. The clear part is the other 16th. Cut it in half. What I just shaded in is half over 16th. Half of, that means times 16th, 1 over 32. This clear spot is 1 over 32. If I shade in half of it, I shaded in 1 over 64. The remaining part is also 1 over 64. Cut it in half. That is, shade in half of that, I shaded in 1 over 128. And if I keep doing this, I'm going to get 1. I'm going to get 1. Okay, so you can add an infinite number of numbers and get 1. So now that, just here's the neat thing, now that you can get 1, a half plus a quarter, which is a half squared, which is 2 squared in the bottom, an eighth, or 16ths, etc. Since this is equal to 1, that is the summation of 1 over 2 to the n, as n goes from 1, because that gives me the half, to infinity. This is 1. How can you get me? Can you give me an infinite series that adds up to 9? The answer is yes. Multiply this by 9. 9 times this summation. Well, on one hand, it's 9 times 1, which is 9. On the other hand, you can bring in the 9, and you get the summation of 9 over 2 to the n. That's 9. That's 9. You want to get 19? Multiply by 19 instead. You can get any constant you want. Multiply by k, you'll get k. You pick k. You want k to be pi? I can get an infinite series to be pi. Once you have one that converges, you can get it. You can find another one that multiplies out to anything. If you have this strange summation, well, not strange. You have this summation of a sum n's, and it gives you 2/3. How can I get 9/7? Well, what do you do to 2/3 to get 9/7? Well, here's 2/3. Let me put it to the right. Here is 2/3. If you multiply it by 3 over 2, the product is 1. And now if you multiply it by 9 over 7, the product is 9 over 7. This happens to be, in here, 27 over 14. If you multiply 27 over 14 by 2/3, you get 9/7. But I just have a very strange way of writing 2/3. It's the summation of an. Just multiply. That is, if you take every term and you multiply it by 27 over 4, and then you add them up, you'll get 9 over 7. You'll get 9 over 7. Just multiply every term in this sequence by 27 over 4. And then when you add them up, you'll get 9 over 7. Of course, I'm assuming that if you add them up before you did anything, you get 2/3. Once you have any convergent sequence to another that converge, have a sequence, a series that converges to other than 0. Because you can't multiply 0 by anything to get 11, for example. I got one that gets to 2/3. Well, now I can get it to be 9/7. Just multiply every term by 27 over 4 over 14. Multiply every term by 27 over 14. Okay, that finishes that section. Good luck with it.